So when a proton, in this case we have a proton, it moves in a magnetic field at some velocity, it will feel some force, and that force is given by V q v b sine theta. So we saw last time this will feel some force given by its charge, its velocity, the magnetic field around it times sine theta. In this case, the magnetic field that we are considering, it is pointing out of the screen. Okay, this dot means it's coming out of the out of the screen. And in order to find the direction of the force, we use right hand rule. So we pointed our fingers along the direction of velocity and curl the fingers towards B, and the thumb gives the direction of the force. So in this case, so that's the magnetic field, it's coming out of the screen, and let's look from here. So that's the velocity, okay, that's the magnetic field. I curl towards the magnetic field, my thumb is pointing up. So the force on the proton would be up. So this will have force in the upward direction. Okay. So now we talked about two types of forces on a charged particle. So last time we talked about force due to electric field. Now we saw the force due to magnetic field. So both electric field and magnetic field exert force on a charged particle. So if you have electric field, so let's say that's positive and that's negative, and when you have two kind of charges, there is electric field going from positive to negative. If you place a proton here, the proton will feel force in this direction. Okay. So that's the force due to electric field, which is given by F is equal to QE. Now here we saw the force due to the magnetic field. So do not be confused with these two types of forces. Okay. You can have electric force due to electric field, and you can have magnetic force due to the magnetic field. Okay. So let's look at a question, conceptual question. So in this case, there is an electron moving from left to right, and it enters the electric field. Okay, so this part is the electric field. And because of the presence of electric field, the path of the electron deviates, it goes up, it is deflected up. So what would be the direction of the electric field that will produce that deflection? So we have options, all these different options, either whether the electric field is pointing that way or up or to the left or down or out of the page into the page, or none of the above. So which electric field will produce that kind of trajectory? Down? Okay, so let's see if it is right. So you are saying the electric field is down. That means we have positive potential on up and negative potential down. and when the electron is moving that way, this electron will feel the force up, right? Because the positive will attract the negative. So when it's going straight, it will be pulled up because we have positive charges on the top. So it will be pulled up. Yeah. So that's the right answer. So the electric field is pointing down. So that is due to the electric field. Now let's look at the force due to magnetic field. Okay, so let's see. Here. So a proton is initially at rest in a region of constant magnetic field. There are no other charges present. Choose the following possible direction for the magnetic field. What is the
0?
What is the direction of the initial magnetic force? Oh, no, sorry. This is asking for the force. Which way will be the force?
0.
Why is it 0?
It's not moving.
Yeah, that's right. So the proton is not moving. If it is not moving, then according to this formula, I already erased the formula. So we have force is Q VB sine theta. If the proton is not moving, then V is 0. If V is 0, there is no force. Now let's say the proton is moving. Okay. Let's see here. Now it's not proton in this case, it's electron. And in the magnetic field, this is the magnetic field. And when the electron enters the magnetic field, the electron is deviated in the upward direction. In the previous question, we considered the electric field, but now we have magnetic field. So what should be the direction of the magnetic field in order for the electron to move in the upward direction? Should the magnetic field be up, down, huh? Out of page, is that right? Why is it out of page? Opposite to right hand rule, okay. So let's use the right hand rule. So let's look at right hand rule. So that's our magnetic field. And we are saying it is out of page, right? So out of page is that. That's the magnetic field. Okay, and the electron is moving that way. So that means if it is moving up, then that means the force on the electron is up. And the speed is that way. And that's the magnetic field. So use the right hand rule. If your right hand rule is correct, then the magnetic field we chose is correct. Okay. So that's my magnetic field. That's what we are assuming, and that's my speed. Okay. Magnetic field curl around this, curl towards the magnetic field. My thumb is pointing down, so the force is down. But since we are considering the electron, that means we need to flip the direction. So the force is up. Because of the up force, it's deflecting up. That means that's the correct direction. Does that make sense? We are assuming that our magnetic field is pointing out. Okay, we don't know if that is correct or not, but what we know is we know the speed is to the right and force is to the going up. Okay, so point your fingers towards the speed, okay, and then curl your fingers towards the magnetic field. I cannot curl like this, so I need to do like so, fingers pointing that way, okay, and the magnetic field is, let's use a different so that's my V, that's my B. Okay, so V is going to the right, B is coming out. Point your fingers towards V and then curl towards B. Thumb is pointing down because it's electron, so you need to flip that. When you flip, your thumb is pointing up, so the force is pointing up. So that's the correct thing that we saw in the picture. That means the magnetic field we chose is the correct one. Let's see here. Okay, that's the only question we have. So we use right hand rule in two different ways. Let me give you a brief review on where we use the right hand rule, just so that you don't get confused. So we use right hand rule to find the direction of magnetic field. Okay, so right hand rule to find B, and we use right hand rule to find force. Okay, so B, how we use that? Let's say we have some current. Okay, so in this case, you point your thumb towards the direction of current, okay, and then wrap your fingers around the loop, and whichever way the fingers are pointing, that would be the direction of magnetic field. Okay, so thumb points the direction of I, and fingers would be pointing along the direction of B. That's what we saw last time. So let's see if I can find a loop or something. So let's say my current is going that way, okay, that way. So point your thumb towards the current that way, and then wrap your fingers around that. So my fingers are pointing into the screen. Okay, so that means the magnetic field is going that way. Okay, if I choose this direction, then you point your thumb towards that direction. Okay, and then your fingers would be pointing towards the direction of magnetic field, which is coming towards you. Okay, that's the magnetic field. And we also used right hand rule to find force. In case of force, point your fingers towards V and curl towards B, and then the thumb will give you the direction of force. Okay, so do not be confused with these two rules. Okay, so let's look at one more question here. So this is about the magnet. We have a bar magnet, okay, and that's the direction of magnetic field at that cross mark, if that's the direction of the magnetic field, what would be the direction of the magnetic field at point 1 and point 2? Will the direction of magnetic field at point 1 to the left, to the right, up, that way, that way, that way? So which way would be the magnetic field? To the right? Why is that? Why is that to the right? That may be the right answer, but you need to give me the reasoning. How about magnetic field at point 2? Which way is the magnetic field at point 2? Down? To the right? Okay. So okay. In case of magnet, we don't say plus or minus, we say north or south. So we have this bar magnet. That's right in the middle. So bar magnet has north pole and south pole, and we know that the magnetic field always goes from north to south. Okay, so it comes out from north. It always comes out from north and always enters the south. That means if the magnetic field is that way, that means this must be north. Okay, so you see here in this picture, it's coming out. That means this must be north, because it should be originating from the north. So that is the north, and this is, if this is north, then that must be south pole, and in south pole it should be going into the pole. That means yes, so that's right. So at point X, at that point, the magnetic field is pointing to the right. And how about down here? So it's going that way, that way, that way. So what's the magnetic field direction at that point? To the left, yes. So whenever you have this kind of curved magnetic field, the magnetic field at a particular point would be the tangent, okay, tangent line. So you need to draw tangent at that point, and that will give you the magnetic field direction. So here to the right, and down here to the left. That's the direction of magnetic field. Okay. So let's talk a little bit more about the trajectory of a charged particle in magnetic field. So when the charged particle moves in the magnetic field, it feels some force, and the direction of the force in this particular case is given by right hand rule again, because it's a proton, so use right hand rule. Point your fingers towards the speed or velocity, and then curl towards the direction of magnetic field. So magnetic field is out. Okay, so when you curl your fingers towards the magnetic field, your thumb is pointing up, so the force would be up. So when the proton is moving this way, it will feel some force in the upward direction. Okay, so it will be pushed up. So that means it will change its trajectory. So it will change its trajectory like that. At each and every point, it will feel this force, and that force is pushing it up. Okay, when it's pushed up, it moves in this direction. Just like when I throw something in gravity, if I throw straight, what will happen? Earth is pulling the, so if I throw an object straight like that, because of the gravitational pull, this will be falling under the gravity, and it makes this kind of trajectory. Okay, same kind of thing there. So at each and every point, this is being pulled up. Okay, that's why you have this kind of path. And we can see the force at this point again. So which way is the force at that point? Let's use the right hand. So that's the speed. That's the magnetic field. Okay, magnetic field is out. That's the speed. So let's use the right hand rule. Yes, exactly. So point your finger that way, and then curl out. So it's going that way. And that force also changes the trajectory of that particle. Okay, so it curves the path because it's this force is pulling that particle. Okay, and at that point, if you use the right hand rule, the force would be that way. Okay, which will also change the trajectory. Okay, and when it's at the top there, here, so that's the velocity, and then you curl out, it's pointing down. Okay, so the force is pointing down. That changes the trajectory. So each and every point, the proton is exerted some force, and the force is pointing inward. Okay, in some circle. It will make this circular path, and throughout that circular path, the force is always pointing in the inward direction. So that means the proton will make a circular trajectory. And from physics 1, you know, in order for an object to make a circular path, it needs a force. What is that force called? For an object to be in circular path, yeah, centripetal force. So you need a centripetal force. This force is the centripetal force that is keeping the object in circular track. Do you guys remember the formula for centripetal force? There's a formula for centripetal force, which is that, right? mv square over r. So this is the centripetal force. And in this case, the centripetal force is this force, which is the force due to the magnetic field. So that force is due to the magnetic field, which we know is given by qvb sine theta. So this is the magnetic force, and that magnetic force produces the centripetal force. In other words, this force is keeping this particle in a circular track. Okay. Now we have v squared here and v here. We can cancel one of the v's. Okay, and if I rearrange the formula, this equation, and also the angle between v and b is 90 degrees. Okay, so at each and every point you see this is v, and b is coming out. So the angle between them is 90 degrees. Look at each and every point. So that's v, that's b. Okay, 90 degrees. That's v, that's b. Okay, 90 degrees. That's v, that's b. So they are at each and every point, the angle is 90 degrees. So that's 90 degrees. And then cancel v and one of the v's here. Then you get this expression. And you can rearrange this to get that. This is the radius of this circle. Okay. So the radius of the circular track of the trajectory of the proton. So you need to use this for problem solving. Okay, that's yes. Where is that? You want to write the formula for? Oops, that's the formula for the radius. We'll come back to that in a second, but I want to show you the problem first. Let's look at this problem from our worksheet. Problem number 3. Let's choose bigger size. Okay, so we have an electron with some velocity moving in positive z direction, and because of the magnetic field or magnetic force, the electron moves in this semicircular track which has the radius of 0.1 meter. So what is the magnetic field that produces this path, and what's the direction of the magnetic field? Magnetic force, sorry. No, it's magnetic field. Okay. So we want to find magnetic field B that produces this circular track. We know R, the radius of the circle. We are only given half circle here, but it will make a complete circle. Okay, so the radius is given by, what is that formula? mv/qb. Okay, so radius of the circle is mv/qb. Okay, so this q is, you don't need to worry about the sign, you can write the magnitude of that. And we want to find B in this case, so B is, rearranging that, you get mv over qr. So mass of the electron, this is electron, its mass is 9.11 times 10 to minus 31st kilogram. It is moving at 5 times 10 to 6 meters per second. And charge of the electron is 1.6 times 10 to negative 19 coulomb, and the radius of the circle is given, that's the radius of the circle, 0.1 meter. And then if you do the math, you get a magnetic field in Tesla. Now what should be the direction of the magnetic field that will produce that circular track? Okay, let's find the value first, and then we will go to the direction. So what's the value you got? .35 2.85 times 10 to what? Negative 4. Okay, so that's the magnetic field. Now we need to also determine the direction of the magnetic field that will produce the circular track. So look at the original direction of the electron. So electron is moving in the positive z, that means it's moving this way, and because of the force it is deviated this way, that means the force must be pointing that way. Okay, when the electron is moving out like this, it is being pushed that way, that's why you have this path. Okay, so that's the direction of force. So we have force in this direction and velocity outward. Now which way is the magnetic field? When you cross V and B, that should give you that force direction. Which way, sorry? It cannot be into the page because this velocity is into the page. Velocity, force, one thing you need to keep in mind is V, B, and F are always perpendicular to each other. Okay, they are always perpendicular to each other. That means it can be either up or down. Okay, so one is to the right, other one is to out. So B must be either up or down. So let's choose both the cases, okay, and see which one is correct. So let's consider it is up for a second. Let's see if that is correct. So point your fingers towards V. V is out, and then curl towards B. So that thumb is pointing that way, and that's the force. So thumb is force, and because it's electron, so flip your thumb. Okay, for electron you need to flip, which is that, right? So that means this is the right one. Okay, so again, V is fingers, so fingers out. Magnetic field, curl towards magnetic field. Thumb is force, so force is that way. But since it's electron, so you need to flip your thumb. When you flip that, that's the force, which is the right one. So magnetic field is that, and it is up, or you can also say up means positive y, okay, or positive y. So you can always try up and down, and whichever gives you the right force direction, that would be your right magnetic field. Okay, so that's about the force on a charged particle. But let's say we have a wire carrying some current. So instead of a single charged particle, we have a wire, and the wire is in some magnetic field. So let's say in this case the magnetic field is coming out. This dot mark means our magnetic field is all coming out of the page or out of the screen, and I put some current or wire with a current in this magnetic field, and the current, let's say, is moving that way, and this current will also feel some force. Okay, so the force felt by this current is given by, we can use the same formula that you used before to find that. So in case of charge, we have this formula. So V Q V B sine theta. Okay, we can rearrange this formula. So Q, the definition of V is distance over time, B sine theta. Okay, switch Q and T. So Q, sorry, change the take it down to the Q, okay, T, D sine theta, okay, and then Q over T. By definition, Q over T is current, okay, I D B sine theta, and this D is this distance, okay, the charge moves along this distance. That means it's the length of this wire. So that means the force on this current carrying wire in the magnetic field is given by length of the wire current times B sin theta. Okay, I can write IL B sin theta. Here theta is angle between I and B. It's the angle between this I and B. Like in this case, what's the angle between I and B? In this particular example, what's the angle between I and B? I is that way, B is coming out 90 degrees, right? So I is going that way, B is coming out, that's the angle, 90 degrees. Okay, so with that, let's look at a question to apply that formula. So let's look at this number 4. We have this wire that is 0.2 meters long, and it is carrying 2.2 amperes current, so that's 2.2 amperes. Okay, it doesn't allow me to write there. Okay. So the figure shows 2.2, but it's 2 only here. So you can choose either 2 or 2.2. That's fine. Why it's doing that? What is the force on the section of the wire if the magnetic field is 6 Tesla in all these different directions? Okay, so we need to do the problem for the magnetic field at different directions. So for that's A, B, and C. So for A, the magnetic field is along positive x direction. So that's the direction of magnetic field, and that's the direction of current also. So we know force is IL B sin theta, and theta is the angle between I and B. So what's the angle between I and B in this case? Is it 90? 0, yes. So they are parallel, right? Same direction. So the angle is 0. So sine of 0, what's the value of sine of 0 degrees? Sine of 0 is 0, right? So that's 0. So something times 0 is 0. So that means the force on this wire when the magnetic field is pointing to the x direction is 0. Now let's look at the part B. What's the direction of the force as well as the magnitude of the force when the magnetic field is pointing along positive y? Okay, so when the magnetic field is pointing that way, what would be the force? So force is given by something happened. So you guys can figure that out while I'm doing this. So use this formula. F is equal to I is 2.2 amperes. Okay, L, length of the wire, 0.2 meters. magnetic field 6 Tesla, sine angle between I and B, it is 90 degrees, sine 90 degrees. Okay, so let's do that. 2.64 force is Newton, and what's the direction? Out of page, or you can also say out of page means positive z. Okay, so I think you can do C. C is also in same way you use the formula. So let's look at the next one, this one. Okay, so we have two wires. One is carrying 2.4 ampere current, other one is carrying 1.4 ampere current, and the wires are 0.8 meters apart, and they are 0.9 meters long. So what is the magnetic field at wire 1 due to wire 2? So we want to find the magnetic field, okay, due to wire 2 at this point. So we have this wire and we want to find the magnetic field at this point. So this is carrying current 1.4 amperes. Okay, so magnetic field is given by what's the formula for magnetic field of a wire, long wire? It's mu naught I over 2 pi r or 2 pi d. Okay, so in this case we are trying to find the magnetic field due to this wire. So that means we need to write here magnetic field due to wire 2. Okay, so mu naught is 4 pi times 10 to the negative 7 Tesla meter per amperes, and then I2 is 1.4 amperes, and then 2 pi, distance at which we want to find the magnetic field is 0.8 meters, 0.8 meters, and that gives us the magnetic field due to second wire. Let's call that B2. So can you guys find out the 4 times 3.14 times 10 to negative 7 times 1.4 divided by 2 divided by divided by what's that? 3.5 times 10 to negative 7. Okay, you can do that. Okay, assuming that's the correct one. And what's the direction of the magnetic field at that point? Again, use the right hand rule. So point your thumb towards the direction of current and then wrap around it and see at that point where would your finger point. So when you curl like that, your fingers coming out of the page. Okay, so that's out of the page. Okay, now let's look at the second one. What is the force per unit length on wire 1? So this magnetic field now will produce some force on this one, because we have this wire, okay, 1, this one is in magnetic field which is coming out of the page. Okay, so this is now in the magnetic field given by that value, and because of that magnetic field this current will feel some force. Okay, and that force is given by, the force on that is given by the formula that we just used. So I L B, that's the field that is producing the force, sine theta. So this one is the force on 1, so current 1. So I1 is 1 point, we want to find force on the first one, so current on first one is 2.4 amperes. The length of that wire is 0.9. I'll just write L here because we want to find force per unit length. And the magnetic field is, we found that 3.5 times 10 to minus 7 Tesla. And the angle between I and B, what's the angle between I and B here? I is that way, B is out. B is coming out, I is to the left, 90 degrees. So we want to find force per unit length. That means we can move this L on the other side. So F over L is what we want to find. That is 2.4 amperes times 3.5 times 10 to negative 7. Sine 90 is 1. Okay, that gives you the force per unit length, Newton per meter. And we also want to find the direction. Can you guys think of the direction? That's the magnetic field and that's the current. Use the right hand rule. Point your fingers to the current and then curl towards the magnetic field. Curl outward. Which way will your thumb point? Current this way, magnetic field out. So point your fingers to the current and then curl towards B. Your thumb is pointing up, right? So upwards. Okay. So I think we are out of time. We'll continue this next time. We'll do more problems like this next time. But for now, please complete the worksheet. Just a reminder, our next exam 3 is next Friday. Okay? And on Thursday, we'll be doing practice. So please come on Thursday's class.
What time is exam?
Exam would be at this time, so 9 o'clock.
Wednesday's class? Come on, Wednesday's class.
Yeah, Wednesday we will be doing practice. And for the test, if you need some extra time, maybe you can show up at 8:30. We will start the exam at 8:30 so that you get some extra time. But if you don't need extra time, you can come at 9.